Good afternoon. Thank you for joining us on our call today. My name is Katerina Ost from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Predictive Maintenance Best Practices, Proactive Testing to Reduce Downtime and Lost Revenue. The topic is being presented by Kurt Geeting, the Senior Sales Engineer from Fluke. Kurt has worked for Fluke for 24 years. In total, Kurt has worked 40 years in the industry, consisting of 14 years in test equipment distribution, 4+ years in manufacturing representation, NAED accreditation, level 1 thermographer, level 1 vibration specialist, and power quality SME. We expect today's presentation to last roughly 60 minutes, and then we'll answer any questions that you have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls, which you can see on this slide. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Kurt.
Well, good afternoon, everybody. Thanks for your time and your attention today. I appreciate that. We're going to get started here shortly. So, and thank you, Katerina, for the introduction. So, obviously, the reason you folks are all on the call here today is, I think, in effect, we all have issues with things that are not working or are working in a plant or a building, and everything fails, right? Doesn't it? We haven't figured out how to make anything last forever. So, we're going to talk about how we can predict that. So predictive failure, or preventative failure, if you'd like to call it that, is basically the practice of using proactive testing methods to reduce downtime and lost revenue. So, and I'm sure for everybody on the line, you've been frustrated by things that have happened in your plant or your building in the past. So this should resonate pretty well with you. Okay. So there are multiple technologies. Fluke is unique in the marketplace in that we offer the whole list of these. We call this the pizza pie approach. So what slice do you want to get started with? And we have the entire list. This is year 75 for us, by the way. Fluke was started in 1948 by a guy by the name of John Fluke. So we'll get started. So maintenance practices are kind of an interesting thing. Many companies have been in business for a long time, so they're kind of set in their ways in terms of how they do things. And you know, what we're here to talk about today is possibly a different way to approach a problem or a situation. We're going to talk about some trends, and again, we're talking about these leading technologies. And then, you know, let's be honest. Everything in this world has to pay for itself, right? So the return on investment in the savings piece is probably as most important than anything else. But this type of technologies do in fact pay for themselves, and we'll go into great detail about how. So, which practice is best? So this is an interesting phrase we use at Fluke. What's the cost of doing nothing in your plant or your facility? Well, what do I mean by that? Well, if we have breakdowns and you have lost revenue, the production line shuts down, or I lose part of the use of the building, or I've got to keep replacing a piece of equipment that keeps failing continually, and it's costing me a lot of money to do that. What if you added all those costs together on an annual basis? What might that look like? What we're hearing in the marketplace, typically for most industries, $250,000 to $500,000 easily in additional maintenance costs, because I have no idea when things are going to break. And there's a basic maintenance, and that is called reactive. So here's an example. Now this is a little dated, but it's still relevant. I have a motor winding failure on a pulp and paper plant. So as a result of that, this one's right on the production line and it shuts down and we lose 6 hours of unplanned downtime. We weren't planning on losing it, but suddenly it died, and everything does. Then I got to overnight freight it. Then I have to pay guys overtime or folks to be there. And you know, you start to add up the total amount of cost, and $33,000 on one singular event. So one of the interesting little facts on this is if a 10% reduction in maintenance costs has the impact as much as 40% increase in sales. So if my sales volume is down, if we could reduce maintenance costs, which is an overhead, obviously, and one of these is these unexpected breakdowns, then I can increase my bottom line profitability, can I? And if I continually have these breakdowns, think about it from this perspective. If I'm missing delivery situations with our customer, let's say you're making plastic bottles and your line keeps breaking down and we can't make delivery, might that customer find another supplier? Sometimes yes. And then losing customers becomes a very painful process. So that's called reactive maintenance or run to fail, which, it sounds crazy to say this, and the statistic is pretty true. This is about 80% of the market. So if this is the way you're doing your maintenance today, you're really not alone. However, if you think about it, that's really not maintenance at all, is it? If I just wait for things to break or fail, because everything will, what the question really is when? When is it going to fail? And not doing any form of testing or diagnostic work, you're never going to know. And typically, as the phrase goes, it always fails at 5 o'clock on a Friday afternoon. So we have a lot of negatives there, right? Particularly the higher capital costs and the unplanned downtime issues. And what's the cost per hour of having downtime in your plant or your facility per hour? In some places per minute. It can be extremely high. So the next piece of this, if you looked at this kind of rungs on a ladder, it's kind of the way we want to look at it, is what we call preventative. So preventative really is calendar-based. Example, I'm going to tighten things, I'm going to lubricate things, I'm going to change filters, and I'm going to do it on July 1st every year. Well, that's preventative. That really doesn't have anything to do with the health of the equipment. That's just regular maintenance, okay? And so are you going to find some problems? Are you going to be going out and measuring something with an electrical meter from time to time? Yeah, you are. Certainly better than doing nothing, but it is not predictive. It's calendar-based, which brings us to the last part, and that is the failure piece that we're all going to experience here. There's going to be a certain amount of startup on every piece of equipment, but have you ever gotten a bad motor or a bad electrical device? I hear the stories all the time. Yeah, we have. A lot of manufacturers don't test these things because they're commodity items. So you're going to have X amount of failures right out of the box or right off the pallet. But it will run for some period of time, and then at some point, everything degrades and fails. So if we could find out where we are on that curve and we're getting close to failure with test instrumentation and testing equipment, that's called predictive. And sometimes people call it condition-based. So what we're looking for is looking at the health of the equipment over time with various pieces of equipment to determine where we are in the journey of that piece of equipment. Are we still have lifespan left in it, or are we getting close to the failure point in case we want to pull and replace it before we hit breakdown? And that's the value proposition. The idea that I could potentially eliminate breakdown and catch that failure point at the very point in time when I still have life left in the equipment. So if I can pull and replace it now, I can get that one, let's say it's a motor, rewound, and that'll become my spare versus having it out and out fail. So there's your spectrum. Are we going to do reactive maintenance on a low-cost motor, 5 horsepower, 10 horsepower motor versus predictive? Yeah, we're going to wait for that stuff to break because it's commodity item since it's easily bought. But if we're looking at large-scale device like a 400 horsepower motor, I'm probably going to do predictive on that because supply chain right now is pretty critical. And let's be honest, if I lose a motor of that size, that's going to be extremely expensive. So I really don't want that to happen. So if you looked at all this and put everything together in a big pile, what's the best way to go? Well, it's blended, right? That's a pretty obvious answer. Some things are only going to require lubrication and tightening and replacing filters. Some things are things I'm just going to replace outward. But some things are critical assets that are very expensive. And when they go down, my whole plant comes down or my production line comes down. And then that pain of how much per hour we're down or per day, it really becomes impactful. So not equipment's created equal, right? Obviously the cost of the equipment, the ease of replacement, again, supply chain, right? What's that risk of interrupting my business? That's a big one, right? If you have to think about that. So there's a hierarchy. We're going to have your A assets, your B, your C's, right? The A, the things that are so critical in my industry, those are really the starting point of doing predictive maintenance. And that's where we'd want to start the process of looking at all these things, okay? So a couple different ways to go. Now there is a next step in the process. I'll plug this one for a second. It's called asset uptime based. And it gets into software that has the ability to start to track these things. but software does not measure anything. Occasionally a sensor like a vibration sensor, but a lot of the measurements can't really be done with software. Would rather be done with portable equipment that I can move from place to place and device to device on the plant floor. So that pie chart in blue in the bottom, for those who are visually challenged like myself, I'll read it off. Insulation testing, vibration testing, thermal imaging, power quality, balance and alignment. So that would be shaft alignment balance, ultrasound technologies, and oil analysis. These are all parts of that pie. The only thing that we as a company don't really play in is oil analysis, but everything else we do. So I'm going to build this pie of testing that I'm going to do and be able to predict the failure point. Okay. Easiest one to start, thermal imaging. Why? Well, it's an easy technology to understand. It's easy technology to learn. So again, why do I need a thermal imager? Because we were not created with the ability to see infrared energy with our eyes. Now, if you owned a snake or an owl or somebody like that as a pet, although you probably wouldn't want it as a pet, those are those are things that can actually see that stuff. But we as humans cannot. So we have the optics built into a thermal imaging camera, so we can see the effect of heat. So infrared energy gets emitted off of everything above absolute zero. Everything emits infrared energy. And an increase in temperature is the primary indicator of future failure. As things get hot, they die. Easy concept to think about, right? And what are we going to look at? We would look at the nameplate or the operating temperature of that equipment. Every manufacturer out there is telling you, here's the operating range of my equipment. Easy part about this, we can take an image, we can share that with somebody else, and we can start to document the thermal health electromechanical equipment on my plant floor. Oops. So go back to your physics class, for those who remember that. Mine was a long time ago. I won't tell you how long ago it was. Convection, conduction, and radiation, right? Heat transfer. Heat goes from hot to cold, right? So the overheated motor inside, that heat inside that motor comes the outside jacket. And what we're seeing with a thermal imager is surfaces. Other things will account for the temperature. If I got a lot of wind or fan blowing across the motor, that's going to do convective cooling. Obviously, anything that's got any form of moisture associated with it is going to change some of the temperature measurements as well. So we're going to qualitatively compare two things. And by the way, it's an interesting picture there. If you look into the one on the left, what the heck is that? That's a guy who's looking at himself in a pane of glass, excuse me, a pane of glass. Glass reflects your own infrared image. Plexiglass does as well. But we'll get into this a little bit later and talk about the idea of what's called an infrared window to look into a panel. But we want to look at it while it's loaded, at least 40%. There's no point in doing thermal imaging on a circuit that's dead or a motor that's not running, right? We're going to see that heat when it's on load or there's a load running. So lots of applications. Electrical is probably the number one. And by the way, this year, NFPA 70B, B is in Baker, which is the 2023 version of NFPA 70E, now requires thermal imaging or scanning in electrical panels where you have a certain amount of people in a building. It was highly suggested, and now it's listed as being required under the new standard that just got launched this year. So why are things hot? Unbalanced loads, I have too much current. So for example, the picture that's yellow and purple in the bottom left, that's a picture of three breakers, and the one on the right clearly is a lighter color. That indicates it's hotter, by the way, of course. And there might be more current running through that phase than the other two, and so as a result of that, it's going to get hot. Now, a thermal imager is a great tool. It'll never tell you, though, it's got too much current. So you need to use other equipment to figure that out. A voltmeter, a clamp on, possibly a power analyzer, to figure out what's going on with this electrical circuit and get to the root cause of why is it hot? Why is it hot? See, this is the issue, because we need to fix that, because these heat problems are not going to go away. So you can see all the different variations, substations, motor control centers, lighting, right? And by the way, breakers trip for two reasons, and they are over current and over temperature. So you can have a lot of nuisance tripping on a breaker just based on heat. And if you're out there reading the current with your clamp meter, and you're not using something like a non-contact thermometer or thermal imager, then you're never going to know that it's hot. So you can see how technologies start to play. So what's the inspection? If I'm going to go out and do this stuff, how often should I look at it? Now, again, let's talk about what's the level of criticality of that piece of equipment to you in a plant or building. Well, if I'm running my own substation, and I own it, I better be doing that pretty often. Transformer is probably one of the top ones, right? If the transformer goes down and you drop all power into the building, there's going to be a problem here. Even if you have a generator, that's not going to last forever, run forever. So we certainly don't want to have that happen. Large scale motors, motor control centers, right? Those types of things are things I really want to look at and pay close attention to. Mechanically, why do things get hot? Well, number one is actually airflow, believe it or not. People don't create airflow across a motor or a pump or compressor or those types of things. And that device has to breathe. So those fins that you would see on the top of a motor, those are heat sinks. That's actually designed to help pull the heat out from inside the motor to the outside. And the idea is airflow going across that is helping to cool the motor. So if we don't give it any airflow, or we cover that motor in grease and dirt, it literally can't breathe, and it's going to get hot and it's going to fail. But there are other reasons as well. Obviously, if I've got bearing problems, and interestingly enough, bearing problems are not something that starts out as bearing problems. We'll talk about this a little bit later, but there's other reasons why I have bearing problems. So again, some other ideas. One of the fun ones is the one on the top right, misaligned belt. So this is a tough one. If you've ever used a little handheld non-contact thermometer, well, first off, you're going to have to be right next to this belt. And second of all, you better not drink any coffee. So it's going to be very tough to be able to pick up this heat of that belt. With a thermal imager, we actually see a belt start to fray apart. All belting has a temperature rating on, and I've actually seen this live with a thermal imager where it's literally ripping itself apart as a function of temperature. You can see that live with a thermal imager. So roller bearings, pumps, obviously motors. Again, what are we looking at? We're looking at the nameplate of these devices to determine, am I over the rated temperature of that device. Process applications are big. Steam traps are huge. This is one where I can see a block steam trap. It should have a very distinct hot and cold side to the trap. And if it's bleeding through, it's a defective trap. You're wasting hundreds of dollars of energy per day on that trap. But we can see level in the tank. This is one of the reasons why people want to take these home, because believe it or not, you can see the level on your gas propane tank on your gas grill in the back. So is it time to get that refilled or not? But any non-insulated tank or vessel, we can see the level, and you can clearly see this in this image right here. And that first tank in the front, the orange level is fluid in the bottom of the tank, and the air is at the top. And here's another example. Take a look at the chiller. That's the cold water in the bottom of the tank. The vessel that's sitting above that, I'm not sure what that is, a regular water tank or what have you. But lots of applications, and some of these are not electromechanical, right? I could be looking at pipe integrity. I could be looking at welds. I can be looking at any number of things with a thermal imager. Anything's possible. Last one, this is one that's pretty popular, is finding a leak on the roof. If you ever had to replace a large scale roof, particularly for a manufacturing facility, man, that is expensive. I've heard bills anywhere from $100,000 to $1 million to replace the roof. So what if we could actually find the origin of the leak on the roof with a thermal imager? How's that possible? Well, if you have a crack in the roof and it rains and the water gets trapped into the substrates, underneath the surface of the roof, that trapped moisture typically shows up as that stained ceiling tile in your conference room, right? Well, water follows gravity, not logic, right? It drops to its lowest point. So you can't really troubleshoot a roof underneath. You need to go top down. Here's how this works. In the evening hours, when the sun drops out of the sky, the part of the roof that's dry, i.e. where it's blue, will drop in temperature. But where I have this overheated water that's been sitting on the roof all day long with the sun beating down on it, that heat pattern is going to rise to the roof, and we can actually find the origin of the leak. And you only have to fix the portion of the roof where it's leaking. Imagine the savings of that, as opposed to doing the whole roof. Air leaks, moisture intrusion coming behind the wall. Again, another reason to bring it home, right? Particularly in the wintertime, where am I losing insulation around my windows and my doors? So a lot of home inspectors will use this type of thing, including where you've had moisture damage, and they'll come in and use this to determine, do we still have moisture in behind the walls, and the possibility of mold and things of that nature still growing. So how's this created? Pretty simple. This is an interesting analogy. If you look at it, we've got a non-contact thermometer. So typical resolution these days, if I took those two numbers, 160 by 120, that's going to be tens of thousands of temperature measurements. I want to see the exact number off the top of my head, but somewhere around 30,000 measurements or more. So that's like 30,000 of these non-contact thermometers duct taped together and pointed at something. Very similar to the way your digital camera does. It's a series of pixels put together that creates this composite image. In this case, we're looking at the face of a dog. So, and each pixel is what's called radiometric. So what does that mean? There's an actual temperature associated with every pixel on the display of a thermal imager, and all those are available to be looked at in software. And how do we size and how do we find one? Well, we've created what's called a field of view calculator. There's no such thing as one size fits all. And there's quite a few imagers in the lineup. And the idea here is, what if we could actually customize it to your specific application? So how does this work? So I'm going to say I'm going to look at something 10 feet away, and the spot size I need to look at is going to be as small as a half of an inch. Well, the field of view calculator allows you to pick that out, and we actually ran all the geometry for you already and be able to figure that out. So you're buying the right device for the right application, and there's no such thing as buying too much resolution. It's too little typically. If you buy an inexpensive camera and expect a lot more out of it than what it's able to deliver, then you're going to have what we call buyer's remorse. We really don't want that. We want to have you buy the right product for your application. And this field of view calculator, which is one of the things we have on the Fluke website, allows you to do that. And I believe Transcat has this also supported as well. So temperature, obviously, anything that's got moisture in it, it's going to hold temperature, right? So thermal capacitance. And the last part of this is, how do I look at this safely? So for those who have ever seen thermal imaging done, obviously that panel door has to come open, right? That swings open, and now we're starting to look at things inside the panel. Well, that's all well and good, except if I'm looking at a 480 volt panel with 2000 amps flowing through the conductors, I'm going to have to put a lot of PPE on for that inspection. And let's be honest with you, I don't see people very happy about the fact they have to put PPE gear on, and nobody wants to stand in front of a live arc blast zone. So what if we could mount a window? And the infrared window is exactly what it sounds like. It's infrared. The difference between this and glass and plexiglass is this pure crystal. It allows thermal invisible light to travel through. Now, this is a picture of an older window, but there's about 6 different offerings we have at Fluke. And the idea is that this permanently mounted on the panel. They're 2, 3, or 4 inch size. And then I can shoot inside the panel, and we don't have to be in the full arc blast zone, and we don't certainly have to have the full clava and everything else on. Maybe a reduced amount of PPE or no PPE, depending on where you are, but safely shoot through there, and I don't have to open the panel door again to do my thermal imaging. So huge saving and efficiency play in terms of getting that done. So switching gears, kind of in the same vein as looking at thermal imaging, the other visual product that we're having a lot of success with the last 4 years is what's called an ultrasonic leak detector for doing acoustic leak detection. So whereas thermal would be used for wetted applications where I'm looking for moisture, the II900-910 technology we use for gas or air leaks. So where would I be looking at that? Well, compressed air is probably the number one. So compressors use 10% of all electricity here in the United States of America. Now, compressors can be used obviously also for refrigeration. It's not just for compressed air. But for anybody who's ever run a compressor, and you might have multiples of these, if I have leaks in a variety of connections all over my plant, and we're seeing dozens and hundreds in a plant, then I'm going to lose capacity of that compressor. 20 to 30% is not unusual. And the compressor is going to have to constantly run to compensate for the leak because there's pressure drops now, right? And we're going to drive up our electric bill, and we're going to reduce the lifespan of that compressor, because if you've ever looked in the front of a compressor, it says hours of runtime. It doesn't say years, it says hours. And these are expensive, right? $50,000 plus. So could I literally run a compressor to death? Yeah, you can. And leaks are going to cause that to happen. So we got 3 things going on at the same time if you're kind of hearing this. I've got drops in my pressure, so my pneumatic tools don't work on my plant floor. I'm driving up my electric bill, and I'm reducing the lifespan of this very expensive capital item called a compressor, excuse me, all at the same time. Is this a this is a good idea to do leak detection then? Yeah, obviously. And so here's some applications. You've probably seen some of these things, but you know, in the world of automation now, right? How do they build a car? Top right corner, right? We got all these industrial robots that are all running off of pneumatic controls. Sometimes it's hydraulic, but a lot of it's pneumatic, putting a vehicle together as it's traveling down a production line, right? And that's not unusual. So whether it's a gas leak, a vacuum leak, or any type of gas, we can start to find these things. So here's an interesting little tidbit. And again, these are statistics that we use at the Department of Energy, and we have quite a few of these. You know, one single 1/8-inch leak, 1/8 of an inch leak, excuse me, could be $2,000 to $5,000 a year. And how many leaks do I have on my plant floor? Sometimes, again, dozens, hundreds. Let's multiply that out, right? So that right there, my friends, is the cost of doing nothing right there, that first line. If you want to think about that one, that's where it really, the rubber hits the road. So we want to be able to reduce leaks, drop my electric bill, and increase the runtime or the lifespan of that compressor. And ultrasonic leak detection is a great way to do this. So we call this acoustic imaging as well. It's kind of another way to phrase it, but these colored dots that you see on these pictures to the right basically is how we do this. So the sound image is overlaid. So we've got a high resolution camera surrounded by 64 sensors. And the way it looks at it and does this, what's called a sound map. So it actually maps these, and believe it or not, we can triangulate to the distance of the leak. We're going to superimpose that visual image right on the display, so I can see the thermal, the leak, along with where it's coming from, and a variety of other metrics, one of which is the severity of the leak. We can put a pressure typed in on it. We can actually establish cubic feet per minute, and we can monetize a leak. So if you've ever done leak detection, this is a very tedious task. And for those who've ever used what's called a snoop bottle, which is where you're basically spraying fluid onto a pipe to determine if it's going to bubble up, and how many thousands of feet or miles of pipe do I have in a typical large process plant? It's going to take you forever to do that. The older methods of using ultrasound detectors with headphones has been a standard in the marketplace for a long time, but the problem is it's point by point and very meticulous, and you're going to hear all the noise through those headphones. There's no ability to really filter any of that out. And if you've got a leak that's 25 feet up in the air above you, you're going to have to get in a lift truck to see that. There's no way you're going to do that. So you're limited distance, and you really have to kind of learn sounds that you're listening to. Acoustic imaging, we can see 150 feet away, we can start to see leaks. And we can capture that image, we can tag it, and we know it's a real leak. And one of the ways we do that is we can see if the leak moves when we move. And if the leak moves when we move, it's reflection. That's something you would never know with headphones because you can't see it. So we can determine these are real leaks, and we are going to tag them. All right, moving right along. So the last two technologies really get into more the mechanical side of the house more than anything else. So mechanical vibration, which is a big topic these days, is a way to determine that I have a mechanical breakdown within my rotating device, like a motor, a pump, a compressor, a fan, a blower. And the reasons that I will have mechanical breakdown are actually listed at the very bottom, that last line. Bearing conditions. So bearing conditions start out as good, but then because of shaft misalignment, looseness, and unbalance, it becomes a bearing problem. So bearing problems don't start out as bearing problems. Bearing problems start out as something else and then become a bearing problem. So when you're doing vibration analysis, we need to consider all these other root causes of why I have failure. So of all these slides I'm going to show you today, this is probably the one that has the biggest impact, and we really want you to think about and look at this one for a second. This is the standard way that most electromechanical devices like a motor die. And we know this is a very repeatable phenomenon. So I can have a vibration change on that rotating device as far as 9 months out. And I'm starting to see higher bearing frequency noise with the vibration analyzer and know that, hey, the end is coming. If you're doing wear debris sampling in your oil, i.e. screening, and I'm looking for metal particle breakdown, which is clearly an indication there's something going wrong here, that's 1 to 6 months. The thermography piece, where that overheated condition inside that motor starts to come to the outside jacket, keep in mind, thermal images can only see surfaces, it's not X-ray inspection, is 3 to 12 weeks. Then we cross over an area, which I'll explain a little bit, is what's called power factor efficiency starts to drop. So I'm now, if you think about it, I've got a mechanical issue, I've got a thermal issue, and now I'm electrically unstable and I'm starting to waste energy at 5 to 8 weeks out, and then 1 to 4 weeks out as the audible noise. So a lot of plants, we used to have the guy, we call him Old Joe. He had the stethoscope, the screwdriver, the wooden dowel, and he was putting that up to his ears and he was listening. Well, if you can hear it with your human ears, it's too late. It's going to go within 1 to 4 weeks. And if I put my finger above the bearing and it's burning off the end of my finger in the course of about 2 seconds, it's going to go within days, and then it fails. So if I know when things are going to fail and I use a variety of technology to determine it, you can see how easily it would be to be able to set up a program to figure out and predict the failure point and when we need to pull and replace that motor on a production line before it fails. So again, a lot of the same stuff we looked at with a thermal imager. Okay, so why is it hot? Vibration. So vibration can cause heat. Thermal imager shows me it's hot, but I don't know why it's hot. With the vibration analyzer, I can see why it's hot, and we can get to what we call root cause. So bearing failures, misalignment. That's where the shafts of a motor and let's say a pump are not aligned properly. Things are unbalanced, right? Use an example. I've got a fan on a blower, and there's a whole lot of dirt on one of the fan blades, and it starts to wobble. That's what's called unbalance. And then looseness. I've seen a lot of this in the market. It's crazy. People will use a variety of things for shims underneath the foot of a motor, including cardboard, which doesn't really hold it down to the floor. So the motors do a little dance every time it rotates, and that looseness eventually translates into a shaft misalignment, which translates into a bearing failure. So it's kind of what we call a domino effect. Here's the reasons why. Okay, and so yes, bearings do fail, absolutely do. And this is what's going to basically kill the motor. But again, why are they failing? That's the important issue. Why are they failing? Can we get to the root cause and fix that and decrease the speed at which that bearing is failing, or stop that failure problem in its tracks? Okay. Misalignment is responsible for 50% of all bearing problems. So you can be off slightly in the middle, from side to side, angular or parallel. You can see everything has to be lined up right on top of each other. And the most critical part is if you're running a motor or anything that's running at a high RPM or high speed, that tolerance is going to be super tight. And that's really tough to do with a gauge or a straight edge. It's going to require a higher level troubleshooting device to figure that out. So misalignment, here's all the reasons things move. One of those is temperature growth, right? A variety of things can lead to misalignment. And then the unbalanced piece. Again, I get the dirty fan blade. Any number of different reasons can start to create the unbalanced situation. And now I've created this unbalance, which also starts to create a bearing problem. And then looseness. And rotating, non-rotating, right? So the foot and the foundation, we call loose, soft foot or loose foot. It's one of the diagnostics. So vibration analysis gives me an instantaneous measurement, tells me the condition of the machine, where we are in its lifespan, and identifies the root cause. So if you've ever seen anybody do this stuff, it's pretty involved. As a matter of fact, I'm a vibration specialist. I'm a level 1, which is like a business degree or a BA. Level 2 is a MBA, and level 3 is a PhD. These folks make a fair amount of money, and they're very costly to have come on site. And certainly can't afford to have them go look at everything. But they're going to look at what's called squiggly lines, for lack of a better way. It's called a time waveform, so it's amplitude versus time, which you might see in an oscilloscope. But then they're going to look at amplitude versus frequency, which is called spectra. So they're actually trained in looking at those waveforms to determine the problem, and they do it based on all the math that they know. So not everybody has that kind of time to learn all those things. So what if you had the ability of knowing what that guy knows in your palm of your hand? And we call that a Model A10. And the concept is we've actually recently bought the company called Zima DLI, and we had borrowed their, I shouldn't say borrowed, but paid for their intelligent baseline. We have 10,000 devices already built into our box. So we know what good is. And if you know what the good signatures of these things are supposed to look like, you can compare it to the one that you're currently testing. And now get to root cause, severity. Where am I in that 1 to 100 severity scale, i.e. how soon do I need to pull that motor off the plant floor? And the location of the fault, where's that problem coming from? So again, lots of data to look at, and lots of math to run, and a lot of waveforms and frequency analysis. But rather than having to learn all that stuff, what if we can have a box in your hands that'll give you all that within 8 to 10 minutes? So this is a self-guided box. This is one of those that customers don't have to read the manual on. And we're trying to do a lot of that. It allows me to set up the instrument, diagnose it. Here's all the things I need to know. Okay, so the pump, is it an AC or DC motor? Is it attached to variable frequency drive or not? What's the frequency of the RPM speed? What's the horsepower? How's it mounted? How's the bearing type? Is it overhung or is it roller bearing? What's that coupling look like? And what's the other driven device? Is it a pump? Is it a fan? Is it a blower? Is it a compressor? What is it? And we developed a drivetrain, which is that picture right there. We either with a magnet or with a stud mount or drill into the housing of the motor, mount our accelerometer. So what an accelerometer is, this round cylindrical thing here on the end, is a sensor that measures vibration, and it does it in 3 axes. So axial, tangential, and radial. So we're looking at, across the top of the motor in relationship to the shaft, and then running side to side and up and down, and allow you to see that movement. At the end of testing all 4 points, so we do the non-driven end of the motor, the driven end of the motor, go across the coupling to that driven end of the motor of that pump, and the output, the bearing of that pump, if you can get to it. We're going to show you what's the problem, where's the problem, and how bad is the problem. Thinking about it is years, months, weeks, days, right? When we get to the end of the orange, the beginning of the red zone, we're going to start to think about pulling that device off the plant floor, right? If we drive it all the way to the point where it seizes because of extreme bearing failure, then you may not have any life left in that motor. So we really don't want to do that. We want to pull it when we still have life left in it and can be reworked or rebuilt or rewound. And then we use that as the spare. We replace that motor with a new one, but we don't keep buying motors. So the idea is, what if we reduce our spares inventory as well? So this thing gives you everything you need. I'm not going to read the whole list, but everything you want is in one box. One part number gets the whole thing. We do include software. And it's a very powerful tool. We sell a lot of these. We allow you to track this particular product with something called viewer software. And this is basically a database software that tracks the historical measurements you're taking with the A10 over time. The idea, the concept is, it tracks it based, if you see the picture on the left side of that screen, by color. So red, orange, yellow, green, and ranks order them by their worst case scenario. So the ones you're going to look at that are going into the failure mode, we want to look at more often. We do allow you to integrate things like a thermal image into the same software, so I can see the heat effect with also seeing the vibration measurements at the same time. So machine setup can all be done in the software and downloaded to the instrument, or you can be doing it on the face of the instrument and set it up off the keypads. And then we track everything, give you all the funny lines like your vibration analysis would, and give you the final recommendation, and dumps it out to a PDF. So that's a complete system in the box, basically. One part number gets the whole thing. And allows me to start to get an idea what's going on with my mechanical rotating devices. So again, I mentioned an ROI. So here's a calculator we actually have, where what you can do is actually drop in all these costs of downtimes, again, the cost of doing nothing in the first part of this calculation, and figure out what that looks like as an annual basis. $805,000, that's not an unusual number. I've seen that higher. And what's the cost of buying this? And you know, we don't have to capture every instance, do we? We only have to capture enough to pay for ourselves. Everything after that is savings, right? If you think about it. So last but not least is power quality. So power quality and power quantity are something a lot of people know some things about, but we're going to spend a little time going through this and give you guys some ideas of this. So the first part of this is, you know, we like to equate power to a glass of beer. It's kind of an interesting thing to think about, particularly at 2 o'clock in the afternoon. So the transformer outside your plant is in kVA or kilovolt amperes. The beer you're using is kW. The kVARs are the wasted energy of the suds. So what is power factor or efficiency? Power factor is kW, the part you're using, over kVA, the part you're as available to you. However, you are paying for the kVARs, or the wasted energy, which kVARs traditionally show up as a form of heat. And we don't want a hot electrical circuit, right? So first and foremost is power quantity. You know, where are all the energy hogs in your plant? If things are wasting energy, they're probably running inefficiently. And they're probably also a candidate to know that something's bad's going to happen soon. So as we start to increase power usage on a particular device, that's a red flag indicator that that piece of equipment is not functioning at its optimal level and may fail soon. So typically what happens is devices start to draw more current, or their power factor efficiency starts to drop. And we can start to see that with what's called a 3-phase power analyzer. So demand is the instantaneous number you pay from the utility. They look at your usage every 15 minutes, and you know, who's driving up your demand charge these days. Another thing to be able to look at with a power meter. And power factor efficiency. Most customers are trying to shoot for 0.9 or 90%. And if you're buying power at medium voltage, i.e. above 1,000 volts, and you have your own substation, utilities typically will hit you for a power factor penalty if your overall bill percentage-wise drops below 0.9, and that can be 5 to 10% on top of your normal bill. So that gets kind of expensive after a while. So demand, consumption. So you think about kW as the speed, and kilowatt hours is the distance, right? So you're going to have all this sitting on your bill. And the peak demand is done every 15 minutes. So they look at your maximum draw on a 15-minute average. And if you go above the expected number that you and the utility agreed upon, you're again find yourself in the penalty box, and you might have another 5 to 10% on your whole bill from that time on as a peak demand charge. So this stuff can get expensive after a while. Who's causing this, and where is this all happening, and why is my bill so big? So the idea of examining your bill, let's see where your wastes are and how much you're paying in these penalty charges. And let's start looking at where that's coming from. So if you're going to do a major load change, National Electrical Code says, hey, you're going to run this for 30 days. So you can't do that with a voltmeter and a clamp on. We're going to use a power analyzer to do that with. So where are the biggest loads and the biggest waste? HVAC, motors, and drives. For those who've done lighting upgrades, that's good. But lighting is, in general, for any building in the United States, is 15 to 20% of your load, maybe. And if you've cut your bill in half, you're affected probably 10% or less. 65 to 75% of the electrical use in every building in the United States of America, with the exception of your house, is electromechanical loads, motors, pumps, compressors, fans, blowers, you name it. So a portable power analyzer, which we offer quite a few from Fluke, gives me the ability to go see who's using what. Right now, you have visibility at your switchgear or from your electric utility bill, but most folks don't have any visibility at 3 or 4 or 5 panels down how much an individual load is using. So the idea here is to move it around from place to place and load to load and figure out who's using what, right? So where are the ways I can, you know, fix this? Well, you know, there's lots of ways I'm using energy, but we could do some practices to reduce that. And one of those is looking at older, worn or faulty loads, compressor air leaks, worn pump. Older, inefficient electromechanical devices like motors can be replaced with newer, more efficient versions and pay for themselves based on energy savings, typically within 1 year. Just like lighting. Here's the difference. You start looking at 100 horsepower and above and replacing with higher efficiency, there's a huge impact to your bottom line bill, absolutely huge. particularly when you start to get into 200, 300, 400 horsepower stuff. And so a power analyzer is the only way to really figure that out. How much are they using right at that individual load? But power quality is the last piece of this, and that is how bad is the quality of my voltage? And there's a whole series of measurements in here. I won't get into every last one, but harmonics are the big one. We now use power very non-linearly. We are not making linear power supplies anymore. We make non-linear power supplies. What is he talking about? Switch mode power supplies. So every PC, every printer, every display, everything electronic now has a capacitive diode circuit and basically gulps current and causes harmonic distortion of the current waveform, which eventually can distort the voltage as well. Harmonics create a whole lot of heat and failure in the neutral conductors, which is why we have the super neutral. Makes your motors and transformers run hot. So harmonic content is here to stay. We can't make that go away, but can we identify how bad it is and can we mitigate it to some degree? Well, we can. Dips and swells, it's almost what it sounds like. Voltage is taking a nosedive, it's going high. These are really fast events. These are typically anywhere from 8 to 50 milliseconds. So the way we do with a power analyzer, it's based on the oscilloscope platform. We actually measure each swing of every AC waveform. For those who don't know that, 1/60 means one swing of an AC waveform. In terms of time, is 16.66 milliseconds wide. We can capture events and occurrences with a power analyzer down to 1 millisecond. So the capability of seeing high speed of occurrences and events that your equipment is seeing, but your multimeter and your clamp meter are not because it's not fast enough, is a real possibility with a portable power analyzer. But that momentary drop of voltage can be seen by 1,000 different devices. And one of the things we see is when I stop dropping power, I'm going to drop my my network connection as well. So how fast am I moving data down an Ethernet cable now? Well, if it's Cat5, it's 100 megabit per second. So if we have a half cycle dropout of 8 milliseconds, I've just lost 50 megabyte of data. I didn't see it, my meter didn't see it, but the machine I have hooked up to did. And if we don't have that backed up with the UPS, you can see where things on your plant floor could start locking up and not working properly. So dips and swells are typical. Transients, or spikes, if you like that term, are high-speed noise, comes in, can get through the front end of a AC/DC power supply and get to your component level and actually take out your components. I've seen a lot of this on variable frequency drives. I've seen burnt traces and windings burnt on motors. Typically, that's a transient. That's a very hard thing to capture, and we have to sample that pretty fast to capture that. And we do. So in our latest series, the 1770 series, we can capture anywhere from 1 mega samples, which is 1 million samples per second, or up to 20 million samples per second, and capture these high-speed occurrences all the way up to 8,000 volts, and see these high-speed occurrences. Why is that important? We want to be able to fix it. So you can't fix what you can't measure. Unbalance. I got too much current on phase A, and as a result of that, my voltage is now unbalanced. And a lot of loads are not going to like that. Your variable frequency drives are not going to like that at all. They want to have 2 to 3% unbalance, and if you present more to that, they're not going to be able to compensate. The drive will drop voltage out to the motor. The motor will pull more current. The drive will trip. We will all blame the drive. This had nothing to do with the drive. It had to do with how balanced the voltage and current were going into the drive, and the drive couldn't compensate for that. So keep swapping out drives because you keep having these tripping effects. That is a band-aid approach. You're really never going to get the root cause. And the use of a power analyzer starts to quantify, was a power quality related problem, why the drives keep tripping. Okay. Last but not least, what we call flicker. Sounds innocent enough, flicker. The lights are flickering, right? Well, why are they flickering? A lot of it, again, does relate to what we call startup current. So it's called inrush. So I got a big arc furnace or large motors turning on and off. They can draw 2 to 10 times normal running current, what we call inrush or peak current, and cause a momentary drop of the voltage. And then the very sensitive devices you have around the plant floor are shutting down, of course. And one of the fun ones we're seeing is unwanted triggering of the UPS all of a sudden kicks over to battery mode with no reason why, and people scratching their heads on that. So we can see these events, we can quantify these events, we can capture these events for power quality and power quantity at the same time. Lots of things we're going to look at. There are lots of solutions out there and ways to mitigate the problem, make it go away. So again, you can't fix what you can't measure. We can measure, we can quantify and find the right solution and fix it with the right solution the first time and make the problem go away. Last but not least, the standards in this this is a long time coming. If you look at it, we started in the 1930s, but the latest standards are called IEEE 519 and EN 5160. Here's all you need to know. If we tell it what the nominal voltage is on the line, i.e. I program my power analyzer to say it's a 480 volt circuit, these standards are already built into the instrument. So they're actually going to be able to establish you've got power quality issues, which really is the quality of the voltage on the line. It's really what we're talking about. And do I have problems and issues with that? Okay. So where do we use these? Frontline troubleshooting, load studies, power quality studies. I'd like to blame the utility, right? Wouldn't we all, right? We can prove those types of things, but you're going to want to do it right off the secondary side of the transformer. That's the only place you can really blame them at, but we can do that. And then energy optimization. Again, we've done the lighting. That's great. What's next? It's all your older electromechanical loads in the basement. Let's go see where the inefficiencies are and see if we can replace those with newer, more efficient versions. That'll pay for themselves based on energy savings, just like lighting, except with a bigger outcome. So lots of tools. I'm not going to go into all these, but basically, we have quite a few offerings in this. So ROI and savings, the last part, and that was a lot. Why do this versus not? That's the phrase right now, right? I've been doing this for 30 years. Why change now? Well, first line right out of there, out of the Federal Energy Management Program, 30 to 40% savings over reactive. If we wait for things to break, nobody's giving us a discount, are they? And of course, I've got all sorts of downtime issues, and I'm paying for it dearly with my risen maintenance cost, i.e. the cost of doing nothing. So what's my return on investment? 10 times. A reduction in maintenance costs, 25 to 30, elimination of breakdowns, 70 to 75%. Wow. Reduction in downtime, 35 to 45, and increase in production. So if I have less downtime and have more uptime, and I'm putting more product out the door, i.e. I'm generating more revenue out of my plant. So lots of things, but in summary, a blended approach. We're going to use all different types, reactive, preventative, and predictive. We use best practices, and so you can have a competitive advantage in the marketplace, right? i.e. I'm going to keep my production line up and running so I can meet my customers' demand for my product that I'm making in my plant. Thermography is the easiest way, or quickest, to find problems with heat. Heat's a future indicator of failure. Things get hot, they die. Vibration analysis allows me to see earliest indicator of failure and rotating devices. And then the power quality gives me the ability to start to see who are the energy hogs in the building, what are older inefficient loads, how much energy am I using, and where are the power quality issues that I might be having in my plant that I have no idea that are going on because my voltmeter and my clamp meter will never be able to tell me any of this. So we came to the end, Katerina. That was a lot, right? Yeah. Was there questions? Was there anybody left?
Yes. So
Yeah.
thank you for that presentation. We will now move into the question and answer portion. So just a reminder, if you do have questions, it's in the right in the question box in the webinar controls. So we do have questions. So the first one, does Fluke offer certified training in any/all of these testing procedures?
Yes. So let's address this two ways. Many of the devices, I'll answer it two ways, will come with a certificate of traceability to NIST, i.e. a calibration certificate. Let's start there. And the reason I'm bringing this up is in some of these instances, you may need that. So on a power analyzer, for example, on a thermal imager, even on a vibration tester, you would have that. So I have some level of guarantee of the accuracy of this. Now, certificate of calibration is good for 1 year. You're going to have to get it recertified every year, but initially it would come with that. On the training piece, we handle this a couple of different ways. So there's a whole lot of online training. We do on-site training. So my job, called a sales application manager, i.e. corporate trainer, there's 5 of us running around the country. I cover the whole Northeast from my home outside of Philly up to Maine, and then all the way down to North Carolina and all the way west out to Pittsburgh. So we can do some buttonology type training where it'd be short term, an hour or so. If you want to run a complete workshop where you're going to have 3 or 4 people or more in a workshop, and we're going to be camped out there for 3-4 hours, that would be a chargeable service. But all training material from Fluke is free. So if you only want our training material and you want to train yourself, we can certainly supply that. Where we charge for is where somebody like myself is going to be camped out with you for a half a day or a day. I've done a couple of these where I'm at a large site on multiple devices for 2 days sometimes. But so yes, you can have the ability to have us help you learn the product after the fact. I might point also to the Fluke YouTube channel. We have over 500 videos up there. We deliberately did this. The running joke I always use, and people get tired of me saying this, but 90% of the male population does not read a manual. And that's the reason guys like me have jobs. So we actually thank people for not reading the manual. But most people want to learn visually. Show me a picture, show me a video. We're doing a whole lot of visual learning these days at Fluke, and we have a lot of visual learning materials that we can supply you with the product after the fact to help you self-learn or find some other arrangement, either us coming on site or doing a webinar or what have you, to help you guide you through the application and the use of the product. Any other questions?
Okay. Yes. Which technology is best to start with when starting a predictive maintenance program?
So typically, I think we kind of hinted at the end, but thermal imaging is typically the first shot and easiest to use and implement. Everybody can take a picture. Most of the cameras are fairly easy to understand. We do offer one additional piece, which we can supply through Transcat, and as to get certified as a level 1 thermographer, or level 2 or level 3. We are aligned with a national training organization called the Snell Group. They're based out of Vermont. And we can sell you a seat at one of their classes, either as an online or an in-person class, to get certified as a level 1. So you understand the thermal piece of this, because there's a whole lot of physics if you think about it. So we can all take a picture, but interpreting the image itself is something that you may want to consider getting level 1 certification on. So you're taking all the aspects in and can make a right call in terms of a problem or an issue. Any other questions, Katerina?
Yes. So does the Fluke 801, does that take data from previous reading from various equipment such as thermograph camera and your vibration sensor,
So,
and any other equipment that a facility may already have available for use for readings?
So we're going to build our own database. So we're not going to import one, but rather we're going to start the process on day 1 of grabbing the measurements across all 4 points on that drivetrain and starting to build a database by severity. So we're going to track everything that's red, orange, yellow, green, and that database software called Viewer. What I was showing is the ability to import the thermal image, and we're going to pull that in as a JPEG file or a bitmap image, either one, and we can sync that thermal image from a thermal imager into a vibration analysis report that would come out as a PDF. So that's how we kind of play the 2 technologies against each other. Okay.
Okay. The Fluke equipment that records data, do those devices come with software?
All of it does. So power analyzer, thermal imager, ultrasonic leak detector, and the power analyzers all download the software. Software is standard with those. There is no site licensing. I will say that one more time. There's no site licensing. We have, on thermal imagers, we have Smart View, which you can either pull the data through a USB connection to the camera or through, and some of them, a memory stick. All the cameras from Fluke now are all Wi-Fi hotspots. So the ability to be able to pull the data out wirelessly, we can do that through our Fluke Connect desktop software, which is also free. And we don't site license, which means you can install our software on every PC in the place and we don't care. So the final thing I wanted to say on that, on all the software packages, software updates are free. Firmware updates on the hardware is free. It's an important distinction. And when we supply you a certificate of calibration, for example, in the thermal imager, it's good for 2 years. All the other devices are good for 1 year. Any other questions?
There is not, but
Okay.
if anyone has any more questions, please feel free to email me, katarina.ost@transcat.com. If you want to find out about more Transcat's products and service offerings, you can contact us at 800-828-1470 or visit our website, www.transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and that you can continue to join us for future Transcat e-learning webinars.
Thank you, everybody.
Thank you. Bye.
Bye.